So now we're going to collect some rules for taking derivatives of trigonometric functions. So our sine, cosine, tangent, as well as cosecant, secant, and cotangent. So right here listed are the rules that we want to follow. In terms of which ones to commit to memory, I would highly recommend just focusing on sine, cosine, tangent. Having those down to take a quick derivative will be very helpful for the future. The other three we'll look up as we need them. So there's some nice derivatives here, like the derivative of sine is just equal to cosine, which I know for me when I learned this, I was like, that's too easy. How can that be? And there are a few different explanations for this, but I really like the kind of graphical approach because it brings us back to the definition of what our derivative is. So right here, we have our graph of sine, and I'm just going to focus on from negative pi to positive pi here. So right here, we have y equals sine of x. So now let's say I wanted to graph the derivative of this function. So remember with the derivative, we're looking at the slope of the tangent line. So some nice ones I could look at is at negative pi over 2 and positive pi over 2. If I graph the tangent line, we're going to have a flat line. And when our line's flat, the slope of the tangent line is 0. So if I wanted to plot points for my derivatives at those x values of pi over 2 and negative pi over 2, our output for our function is 0. So what I'm graphing in blue is dy dx, our derivative. Now, let's find some other points. And we could do this elsewhere, like negative 3 pi over 2, that's also going to have a 0, and positive 3 pi over 2, that's also going to be a 0. Now let's talk about the point that's halfway between those. Let's talk about what's happening at the origin. Now, something that's really cool, in my very biased, math-loving opinion, is if we graph that line right there at 0 for the tangent line to sine of x, we are going to have a slope. In this case, it's going to be positive, and it is exactly equal to positive 1. Now, it's a little tricky to see that here because our scale is a little off here with pi over 2 here and 2 units being 1 along there. So it's not going to look like a nice going through exactly 1 unit showing up on our graph because our units are scaled differently for x and y. But if you did have a nice kind of a scale of 1 and 1 for the x and y axis and you graph this tangent line, it's going to right here match up with the line y equals positive x. So right here we're getting a slope of positive 1, which would mean up here we would have a coordinate for our derivative function. Now at pi, we have the same thing. The rate of change there is going to be a 1, but in this case it's going to be a negative 1 because we have a decreasing slope. So we would be plotting our point down here. And then at 2 pi, we'd be back up at positive 1. And over here, at negative pi, we would have a negative slope, so that would be a negative 1. At negative 2 pi, we'd have a slope of positive 1. And if we connect the graph of those points that we just plotted, and if we got some other slopes that were in between, our graph would look like this, which is the graph of our cosine function, which I think is just so neat. So when we take the derivative, what we're graphing is just cosine of x. So derivative of sine of x is just equal to cosine of x. And we can see that with the graph. Like I said, there's other proofs out there, but I kind of like the visual of this one. So now let's say we did the same thing, but with cosine of x. So down here we have a graph of cosine of x. And let's say I grab those zeros first. So all of those spots where I would see a tangent line that would have a slope of 0, which I say is happening at those peaks and valleys there. So we're going to have zeros at 0, pi, 2 pi. Negative pi, negative 2 pi. And then what we could do is find those spots where we have slopes of 1 coming through. So at negative 3 pi over 2, if I imagine my tangent line, that's going to be my slope of negative 1. So we'd be down here. At negative pi over 2, we'd have our slope of positive 1. So we'd be up here. And at pi over 2, negative 1. At 3 pi over 2, positive 1. And if I connect those dots, we're going to get something that looks like this, which is a transformation of our sine function. So I'm taking the derivative here. It's not exactly sine, because what sine should do is when we're going through the origin, it starts by increasing up and then going down. But we're starting by going down, then going up. So what we have is a reflection across the x-axis, which means we multiply the outputs of our function by a negative 1. So what this will look like is we're seeing sine, but we're seeing negative sine of x. And that right there is how we could see our derivative rules for sine and cosine. And it's good to be comfortable with the graphs of sine and cosine, and I would say if I'm trying to remember those rules off the top of my head, I go to these graphs and just kind of start sketching to make sure which one has the negative, and the derivative of cosine will have the negative sign because we'll have that reflection. Now, our third one that we're going to focus on kind of memorizing is going to be that derivative of tangent of x is equal to secant squared of x. And with that, we could find that using the quotient rule, that the tangent of x is equal to sine over cosine. So what we could do is, if I want to take the derivative of tangent of x, I can apply the quotient rule to sine over cosine. And using what we just found about the derivatives of sine and cosine, this should simplify pretty nicely. So, quotient rule, high d low, so sine of x, except I mixed it up, low d high, low d high, low, and then derivative of sine of x for d high, minus high d low, so sine x times the derivative of cosine x, all over low, low, which would be cosine squared of x. All right, so cosine of x times derivative of sine of x is just cosine of x, minus sine of x times the derivative of cosine of x, which is a negative sine of x, over cosine squared of x. And what we're going to have up here is cosine squared x plus sine squared x. And something we're going to bring through here that might come up every now and then is the Pythagorean identity. We want to remember this one. So I'm going to write it off to the side. This will be a good one to have in your notes from Pre-Calculus 2, which is that sine squared plus cosine squared is equal to 1. That just comes from our Pythagorean theorem and working with the unit circle. So what I'm going to do is make a substitution up in the numerator here. Cosine squared plus sine squared, well, that's just equal to 1 based on the identity. So I have 1 over cosine squared of x, which is exactly equal to secant squared of x. So that's how we can find the derivative of the tangent function based on that right there. All of these others come from rules of reciprocals, using the fact that cosecant of x is equal to 1 over sine of x, and secant of x is 1 over cosine of x, and cotangents coming from cosine over sine. So we could derive each of those. That's not outside of the realm of things we can do, but I'll leave that. If you're very curious about it, try it for yourself. Take those derivatives, use those rules and see if you can get to those answers there. But otherwise, we'll just use these as a reference to look back at. Like I said, try to get sine, cosine, and tangent feeling comfortable. And then we'll go on and use these rules with previously learned rules all together.